In the last few years, we've heard a lot about mimicking shapes found in nature. Forms which borrow design principles from natural patterns might require less material resources, while enabling better performance. The bee's honeycomb, with its high stiffness and low weight, has found its way into aircraft and rockets. Engineering honeycomb today mostly has the same size of cell everywhere in it. It is what we would call periodic, and it is quite like a bee's honeycomb. But nature isn't always periodic. Think about the irregular, seemingly erratic internal structure of a piece of bone, or the cell-like geometries created by the veins on a dragonfly wing. Why are they not precisely periodic? Why bother with aperiodicity? Let's build on this. This is ASU. When discussing cellular materials, we often ask ourselves 4 questions. What is the shape of the cell? How does the size of the cell vary across space? How do parameters like thickness or the curvature at corners vary? And lastly, how do the cells integrate into the larger structure that they fit into? If we consider this honeycomb frame, for example, each cell is hexagonal. The sizes of the cell are fairly constant across the frame. Taken together, these make honeycomb, to a first approximation, a periodic cellular material. But what about a soft sponge? Or a cross-section of bone? Or this piece of engineered aluminum foam? How do we begin to describe these cellular geometries? What these geometries all have in common is that they are not periodic like the honeycomb. They are aperiodic. Let's study these a bit more by developing a classification. In this book called Principles of Form and Design, the author, Wuxius Wang, visually demonstrates different ways of modifying geometric forms and patterns. Inspired by this work, we proposed a classification of aperiodic cellular materials based on modifying a periodic cellular material in 3 ways: gradation, perturbation, and hybridization. Graded cellular materials have a specific aspect of their geometry vary in a deterministic manner in a certain direction. Perturbation, on the other hand, moves nodes around in space with some randomness at its core. Hybridization is a form of aperiodicity where we combine different cell shapes spatially. But how does one, as a designer of cellular materials, work with this? It helps to break down the design into 2 decisions. First, we decide what feature of the cellular material we are introducing aperiodicity into. Is it the unit cell, like the hexagonal cell? Or the member, like the cell wall? Or the node itself, where cell walls meet? And for that selected feature, how are we modifying it? Simply put, the first is a what decision, the second, a how decision. Let's examine this for gradation. For the what decision, we can choose the unit cell, the member, or the node. For the how decision, shown here for the unit cell as the selected feature, we can select from a wide range of parameters that we can change, and also pick a pattern, shown here, that provides the directionality of change of that parameter. Similar approaches can be taken with perturbation, where a key decision is what to perturb, the nucleus or the node. With hybridization, a key question is what cells should be combined? Now, why should we care about aperiodic cellular materials? Yes, they occur in nature, and there are many fascinating questions to answer. Even the bee's honeycomb is not truly periodic. Drone cells are larger than worker cells, and there's a transition in cell size between them. Sometimes you will even find 5-sided or 7-sided polygons because of the way the overall shape is distorted or when combs meet at an interface. But aperiodic cellular materials are also of interest to engineers because of their influence on properties. They are less sensitive to the direction of loading. This is one of the reasons they are used in packaging materials. Researchers have also shown that different kinds of aperiodicity have interesting effects on the stiffness, the strength, and the energy absorption. But we're only just beginning to understand how gradation, perturbation, and hybridization can be used and how to tune the amount of aperiodicity to achieve certain outcomes. We're at the point now where our understanding of nature's structure is deeper than just observing the hexagonal cell of a bee's honeycomb and trying to copy it ourselves. We can take a closer look at the mathematical, design, and even artistic components underlying these forms and their variation in space to drive a deeper understanding. And a deeper understanding can give us a longer reach. This was ASU. Thanks for watching.